Anyway, by the by. So we're carrying out similar set of experiments, only in this case we're going to look at looking at the measurement of the weak measurement for the spin component. So now just a few headlines. Basil, as you know, is I would call him a squirrel at times because he goes wandering off into the stacks at UCL and he just squirrels away, and he says, you know what? He says, Landau and London were looking at something like this for superfluidity, and I went, oh, that's interesting. Anyway, and then, but in fact, because they weren't eigenvalues, they just didn't sort of look at them. They just said, oh, well, you know, we won't worry about it. And Dirac sort of anticipated weak values. Hirschfelter actually called them sub-observables. Berry, as we know, has conjectured all sorts of different momenta. But obviously, Wiseman and Levens, you know, independently noted this fact that they were linked to the bone momenta. But I think what Aronov and Levin really showed us was how not only that, you know, come on boys, these exist, but also how we might measure them, how we can look at them, how we can observe them. And I think that's really, for me, the most important aspect there. So, and these are the various references. I've just put them up there. If you look at my talk, if you're interested in just looking up, the Dirac paper is actually quite interesting. But if you want to look them up, the references are there and you can go for it. And Basil actually will discuss some of this in his talk in about an hour or so's time. Okay, so what have we got? We've got a helium beam. Now we're using metastable. Peter introduced me to the wonders of metastable atoms, and we decided to use helium. And sorry, excuse me. And so we've produced the beam. Okay, so this is a cartoon, obviously, and it's a metastable. It actually comes in two states. One is just a singlet spin zero, but the other is a triplet state, which is the one that we're interested in. So the experiment, as I say, utilizes a metastable state of helium. They are neutral because this is going to be based on Stern-Gerlach magnet, so we can't have a charged particle. And also, this is another lovely feature, is that this state has a lifetime, believe it or not, of 8,000. When I read this, first of all, I thought it was a misprint. I think it's a French group who measured it. I mean, it's a massive measurement to do. But in fact, the point is that when you produce them, by the time you get to the other end, this is the only thing that's left, because everything else has all sort of decayed away. So in fact, it's brilliant for this experiment because it will actually last long enough to go through everything. So, and in fact, this is what it looks like. We just used a simple circular stop to just produce a beam, but these are individual atoms on a multi-channel plate. Oh, by the way, this metastable state comes along with 20 eV of energy in our case. So once they hit the detector, the electron comes off, and the detector registers a hit. So now then, let's get into the real stuff. Right, here we go. So we have, let's just assume we've got one single Stern-Gerlach magnet to begin with. All right, just there. And as the force, I think I should have a minus on it, but basically the force, as we know, is mu dB by dz. And it would, all right, and so it would split into the three atoms, so therefore it would split like this. And in fact, this is our real thing. I call it our traffic lights thing. The reason why the middle one is brighter is because of this spin zero state, which actually is much more numerous than the other three, and so that's why the central one is brighter. But the important one is the +1 -1 there. So we were really over the moon when we actually got this, because it's all right buying this equipment, sticking a Stern-Gerlach magnet in it, but if it doesn't split up, then you're a bit stymied at the outset. But anyway, away we went. So there we go. Now, if you have a second one, if you introduce a second one, then, okay, then of course that would then split, and you should end up with something like that. All right, and this is obviously a cartoon. Now, but this is the strange thing, and this is what the weak value, this is what Aronov et al. Showed us, is that actually if you do two things, firstly, if you make the first Stern-Gerlach magnet a weak, and I'm going to discuss weak in a moment, And also you preset the angle, so you have to pre-select, and you preset in this case by setting this angle. This is the spin angle, theta. Oh, I do like my little flashy signs. And and the fact is, there is a small coupling here between the spin and the centre of mass wave functions. And then if you have well-defined pre- and post-selected states, so here and here, and then what you end up is this small phase change that this weak stage would do, because there will be a small change, but actually it becomes amplified. And what happens, instead of getting the 9 pattern, you actually, at very first, just as you make this, as I say, as it just slightly increases, you actually get this rather strange behaviour where this one, whichever one you've selected, in this case, let's say it's +1, it will move by a displacement which are called delta W. So, and also we put the numbers in for our equipment and for our apparatus, and it turns out that we should be expecting a displacement of about 40 micron. And also what the theory shows is that this delta W will actually have a tan theta over 2 dependence. So it won't just jump to there, it will gradually climb to there as you strengthen this magnet, and so you would, and so you can then have a chance, if you change the angle theta, then of course you can plot out this dependence. Now, like all approximations, there is a limit, all right? And that's true in any branch of physics, there always will be one, okay? And what I want to show, this is a quick resume. If you have the wave function set up, see the transition from the initial to final state and so on. This is the probability mod squared, and then you end up. This is the Gaussian function here, and you can see that in fact you've got z plus ut, where ut is dependent on dB by dz. In other words, this is the standard Stern-Gerlach distribution. You can get this, if you want to look this up for yourself, the best treatment we found is actually in Bohm's book, going back to 1952 or whatever it was when he wrote it. Okay, it's still one of the best analyses of this of Stern-Gerlach, I think. Anyway, but what happens is if you include all the weak measurement apparatus, that actually you end up with an extra term here, which I've called W real. Now I've called it real because you have to remember that a weak value is actually a complex number, and it has an imaginary and weak and a real part. It just so happens in this configuration, the real part depends on theta. The imaginary part depends on the other angle. In the solid angle, it depends on phi. All right. So long as you keep phi under control, then you can measure the real part, or you can get a handle on the real part. And the real part, this is the standard weak value, and in this case, if you put all the algebra in, it turns out to be tan theta over 2. So, and as theta increases, this phase is amplified, and so you will end up with that delta W. Now, the limit we've worked out to, and it's the limit that we've taken to first order, all right, and this is the term, and I'm afraid I'm not going to go through this, but you'll have to just believe me, but it's in our paper, all right. It turns out for us, it's around about 0.37. We have to keep this L at this value, or less than, otherwise it won't work. And what happens is this: if you see this is the +1, whichever one we select, we pre-select, okay, it's 0, obviously it would just be going straight, it would just be going through in the usual way. As you change the angle theta, then it will move to the left. In this case, I've shown it moving to the left, and this is the delta W. But what happens is that if you try and push this too far, it actually starts going back again, which is a bit naughty. You'd think, oh, it'll just get bigger and bigger, but it doesn't. It actually starts going back. And of course, eventually it will go back to the middle. And then of course, if you increase that weak stage, the magnetic field, till it becomes strong, of course, this will then just split into the two states. So therefore, that's the process. And that's why you would never see this normally, because if you did just Stern-Gerlach, you just whack in 100 Tesla per meter magnet, and you would just never see this at all because it's a very small effect. Okay, here's the real live equipment. All right, Mark has told me to buy these from Pfeiffer Vacuum. Marcus? I did. I followed your advice. I'm going to hope you got shares in the company. I presume you must have. Anyway, so but joking apart, we've now built this. The helium comes in here, and it goes through. I just want to mention this while I think about it. If you want to, I'm going to organise a lab visit to Joel's and Vincenzo's lab on Friday. If anybody after the business on Friday, so when we finish on Friday, if you're interested, then just let me know. Okay, and the guys will set them running for us. Anyway, so here it is. This is where it's set up. The CCD camera, the multi-channel plate, and the CCD camera at the very back there, and so the beam set up, and away we go. So schematically, we set it up here. Okay, here we have an electron-seeded discharge. It's pulsed, so we have a pulsar here, and we produce a pulsed supersonic beam of helium star atoms, and of course in the triplet and singlet state. I don't really want to get rid of this singlet state because I think it's very useful to have these ones going through the middle, because in a way it's a kind of like a marker, like a fiducial, to tell us exactly where the middle of the distribution is, and I think that will be quite useful. So we're going to, I can't see any reason why we're actually going to, not to try and get rid of it. We'll just hang on to it. Now, this is where all the business happens. This is where all the various magnets go on. Okay, there are 4 all told. All right, there's the strong and weak stage I just described, but also we need to actually produce this +1 state, and we also need to set the angle theta, and we also need to keep phi under control. So to do that, we're using this combination of a hexapole magnet and a Helmholtz coils. Come on. And this is where the multi-channel plate detector is in the CCD camera at this end. Okay, so just the strong Stern-Gerlach magnet, come on. This is a hefty little beast, as you can see, all right? And this describes how it's manufactured. It produces 100 Tesla per meter. Please, those of you who are not familiar with this, that's not a 100 Tesla magnet. That would kill you. No, well, you wouldn't be able to produce it. It's impossible. But it's the gradient, all right, 100 Tesla per meter, and it's over a 10 millimeter bore size. But believe me, if something gets stuck on there, it's the devil's own job to get it off. So you don't do it. Anyway, and here is, because that's clear, from here where I am, I can't see it clearly. But anyway, you can see the 3 states. Now we've gone from the stop, we've actually got some collimating slits in there, and then that's why you now got this slit, the bars. And of course, what we're hopefully looking for eventually is a movement up here. Now, we've done a fit to this, and as you see, this is the central peak. Again, remind you that this is mostly the spin 0 state. You can see it's huge by comparison, but here are the others. Now, there's one thing I want you to focus on here, and that is you can see these little spikes, evenly spaced. On the front of our MCP, there just so happens to be a grid. It just comes part of it. We can remove it if we want to. Whether we will or not, I don't know. But at the moment, you find out with multi-channel plate. I don't know if you've ever used one. If you have, you'll know that you just don't touch it. All right, not unless you have to, because they break very easily. And it took us a long time to get this, simply because they're all being used to fight wars. Because they're used in goggles, night vision goggles, and trying to get them is difficult. But anyway, the point is, this grid, the pitch of this grid, is of the order of microns. It's something like I think it's 50 or 60 microns. So therefore, that shows us that in fact we can actually resolve down to 40 micron. I mean, it's not easy, but you can see by fitting it and by seeing, and we will be able to see that move quite clearly if we do another fit, and we obviously and do multiple fits. I mean, from particle physics, my job when I deal with particle physics, we do fitting of this nature all the time. It's something we do all the time, so it's not a problem. So the weak stage will be designed to replicate a field of a Rabi-2 wire electromagnet. This is a simulation we've done on console. All right, we're going to produce this locally at the moment. We're not going to, it's quite a simple device, and we're going to calibrate it. And in the college and install that. So that we're underway of just sort of buying the bits and doing that. The pre-selection, as I said, is going to be, we're going to pre-select the m equals +1 state, all right? We're going to use a hexapole magnet, which actually, what it does, it focuses the m equals +1 state, all right? It brings that to a focus, but on the converse, the m equals -1 state is defocused, so we don't have it at all. The m equals 0 goes through. As I say, I feel I want to keep this for the reasons I've already said, all right? What we're going to do is put a copper disc in front, an oxygen-free copper disc in front of this with a slit in it, which will rotate, and that will set the angle theta. Before anybody asks, it's made of copper because obviously we don't want it being magnetic. Otherwise, it will never rotate because it will get stuck to the front if it was made out of iron or something. Right, and then we're going to use a pair of standard Helmholtz coils in front of this or a bit further down, and with that we're going to use that to adjust the angle phi so that as the beam comes out, as it comes out, you know, it's not going to be perpendicular, it's going to be slightly off, and so what we're going to use the Helmholtz coils, we're going to tune it so that we can just basically, you know, get it all lined up. Okay, next one. And so the hexapole was ordered several weeks ago. We are awaiting delivery. They promised us it in the, you know, in the next week or two, and as soon as we get it, obviously we'll install it and hopefully, at long last, do this measurement. So the experimental results which we've done so far, we did a time of flight because it's important to know the velocity. As Lev pointed out, the time that the particles take to get through the weak stage, I think this is the point he was making, the timing is really important. You want to know it, you want to know the speed, and so we needed to do a time of flight measurement. We also, thank us, Marcus, again, we had a diffraction grating by a rather circuitous route, but I know it originated from you, so thank you very much. I would like to be Oliver Twist and ask you if you might give me another one and provide more. Maybe I'll have to buy you a few beers tonight or tomorrow to try and grease that, as it were. But anyway, we've put it through because you, I think, pointed out to me at the last meeting that I need to worry about transverse coherence, as I recall. All right. Well, we've got a diffraction pattern after much huffing and puffing, and then worked backwards from that to show that our transverse coherence to get this was of the order of about 0.7 micron. Now, I want to point out that the collimation system was not optimal for this exercise because unlike with Ephraim's, you know, when you're just doing stuff on an optical bench, you can just move it around. When you want to move something in a vacuum chamber, you have to re-engineer everything. You know, so we just went with what we had because it was sufficient to get this and it was sufficient to show us. And we need a transverse coherence of the order of a micron. So we felt that we've proven to ourselves that with suitable engineering, we can actually produce that. I would like to actually re-engineer it and do it again, but Peter pinched the damn thing off me again, which is why I'm going to come scrounging. I'm standing up. Okay. So hopefully, so now we've built this apparatus, and obviously we're very close to actually getting the weak value spin and measuring this tan theta over two dependents. We want to then obviously we want to use this equipment beyond this. We want to actually go on and look at the imaginary part of this weak value. You remember Basil was talking about the osmotic momentum. I know this isn't momentum, but this imaginary part, and it turns out for this system, that's very much dependent on phi. So with the Helmholtz coils, it will be reasonably straightforward to actually adjust that angle, and so we're going to look at that. And we're also proposing, and Basil's already discussed this earlier, a new experiment, which was this carrying out experiment with two strong Stern-Gerlach magnets to observe the no-crossing theorem, and hopefully prove that the quantum potential exists. Although, in fact, obviously we just learnt that, well done, you already maybe proven it okay, but never mind, good. So, and that is an experiment which we propose for the future. As I say, Basil discussed this. It's on a poster outside if you want to look at it. Okay, with conclusions, just quickly, All right, so we've carried out full analysis of the experiment, which took a long time on my ad and simulations of it. And Vincenzo, I have to say, did an excellent job on working all this out. Okay, we've calculated what our shift should be for our apparatus. We've done these various experiments up to these preliminary experiments, and I think we've proven to ourselves that we can actually do this and actually observe this value. And we have 3 experiments planned. The one which we set out to do, which Vincenzo will write up for his thesis, and that will be hopefully get his PhD from that. And then the other 2, we're going to go further on. And if you want to look for further details, we got a poster, but also we've got a paper on the archive, which we've yet to update, but we're slowly updating things as you do. All right, this is the team. Just a quick mention. Okay, there's Vincenzo there. You see him around. Do chat to him. All right. And lastly, just to mention that a member of the group that's just joined us, Lyndon, he's come on board and he wants to try and look at the quantum potential in relation to gravity. And he also has a poster up, which is, he's literally been with us a few weeks, so it's a very early review stage. But that's another plan for the future to see whether we can use matter interferometry, perhaps. But anyway, that's a bit for the future. So, last of all, the apparatus is currently set up with a strong Stern-Gerlach magnet in it. So if you'd like to come and see it, we can arrange a visit. I've negotiated with Jan that we would do this after the talks tomorrow, about 5 o'clock, 5:30? 5:30. 5:30. Okay. We obviously, as maybe you all know, I don't know, but UCL is basically over the road, so it's a 2-minute walk. So come along if you wish, and if you do, and it all goes well, they're saying you should never work with children and animals or something. This is what actors always say, don't they? Well, you should never work and promise a live experiment, all right? Because tomorrow something will go wrong. Hopefully it won't, but anyway. But if you do, come along, and hopefully this will work. Is it going to work? Come on. Yes. Right. This is actually a film. This is a live film. Not live film, so this is a film. All right, this is obviously the atoms. This is 10 seconds worth. It's actually a lot longer than that. We've compiled all these images, but this is how the atoms come in. These are individual atoms striking, and as you can see, I think you can see quite clearly, these are compilation, so it's a little bit off there, but you can see these coming up. And you would be able to see this tomorrow, but obviously not as many, but you can see them quite clearly. When Vincenzo put this on for the very first time, and we sat there and watched, and we saw these atoms coming in these 3 distinct areas, I went into Strictly mode and started dancing around the laboratory. I'm sorry, I'm sad, but that's just the way I am. Anyway.